I've been working on environmental thermodynamics for about 5 or 6 years. I began because I had an interest in biochar, and I devised several ways to make biochar, and I did several experiments with it, and I worked with it for two or 3 years. But I felt that I really needed some more general information about the science of how soils work, and that kind of expanded into the ecology and thermodynamics, and so I wound up where I am today, never having finished what I started out to do, but always progressing to the next stage. So I'm very interested in the thermodynamics of the environment, and very central to that is the concept of entropy. Now you may be familiar with entropy, but I'm going to go over some aspects of it. Just to try to give you some new ideas that are fascinating me. The fact is that originally thermodynamic scientists felt that entropy was ever increasing in the world, and so there was nothing for the world to do but become more disordered. Entropy is disorder, so there was nothing for the world to do but become disordered, and order would eventually vanish from the universe, and there would be nothing left but this chaotic, disordered system. As it turns out, that's not necessarily so. Modern thermodynamicists feel that entropy is a mobile substance, and it can move from one system to another system, and when it does, the system it moves to becomes the disordered system, and the system that it moves from becomes an ordered system, and it flows just like any other thermodynamic quantity, and in order to remain ordered, a system has to discharge the entropy that it creates. And so I'm gonna go into entropy flow mechanisms first, and then if I can get back to what I was going to give you tonight, I'll do so. I see a sign here that says my battery is running low. I'm surprised it says that because I'm supposed to be plugged in. Let me just make sure. Okay. I'm going to assume that I am plugged in. So, entropy flows from system to system, and I just want to give a few slides that describe how that happens. So entropy, as you know, is the scientific word for disorder. It's closely related to energy, and the formula for entropy is S equals Q over T, as you can see on this slide. This is heat divided by temperature. So if you want to know the entropy of a system, if you can determine how much heat the system contains and divide by the temperature, that's the amount of entropy in the system.
So how do you measure the heat if not by the temperature?
Oh, you have to. There are entropy tables that tell you, how much entropy there is in each material at each temperature, and it's a rather complex engineering process. You have to go to the scientific data to figure it out.
Okay.
But so in general, you can add entropy to your system by adding heat to it. But the higher the temperature, the less difference it makes. If you look at the formula, Q over T is a smaller number as the temperature goes up, and Q, the amount of heat, is the primary determinant of how much entropy there is there. So if you add entropy to your system, it becomes disordered. If you take entropy away from your system, it becomes ordered. As an example, ice is a more ordered material than water. The molecules of ice are attached to each other in a fixed relationship. And so they can't readily move with respect to each other. The bonds are strong and hard to break. So they form a strong self-supporting structure, and they retain their shape. They are solid materials. That all makes them a low entropy material. Ice cubes are solids. They are low entropy. Water is less ordered. The bonds in liquid water are not so strong, and they can slide against each other, and the water flows, so that they are not in fixed positions, but flow readily over each other. The bonds are relatively weak. Water will not support itself. It has to be contained in a glass or some other structure. So it's a disordered material, and the entropy content is high. When you have two identical systems, they have equal amounts of entropy. Two glasses of water with the same ratio of water to ice. Entropy can be transferred from one system to another by removing material from one and putting it into the other. If you take the two glasses of ice water on the left here, and you take the ice out of them, and put all the ice into one container, and put all the water into the other container, all the entropy from the water goes over to the container that contains the water, and the entropy in the ice goes into the other container. But the ice is a low entropy material. So the glass on the right has less entropy than the glass on the left. And it's just a matter of transferring the material to get that entropy transfer to take place. Entropy can also be transferred from one system to another by removing energy from one and putting it into the other. The two glasses again. Let's see. There's a there. Does that show on the? Yes. If I have a heat pump and I circulate water through the heat pump from one of the glasses and extract heat from it, it returns to the glass colder than it was when I took it out, and gradually that glass freezes. If I extract the water from the other glass and pick up the heat from the heat pump, eventually that glass warms up more and more and the ice melts. So I wind up with essentially the same situation I had before. All the entropy has been transferred from the glass that has the ice in it to the glass that has the water in it. And hey, how are you, Rudy? So you can transfer entropy from one system to another by moving material or by moving heat. Now, I'd like to just interrupt here, because if you look at the Earth system, there is no matter coming into the Earth system or leaving the Earth system. But there is energy coming into the Earth system and leaving the Earth system. So the extraction of matter to move energy out of the Earth system is not an option. So it's the energy transfer that determines the entropy on the Earth system. The extraction of matter is not an option, but the extraction of energy happens all the time. So let's go on a little further. In thermodynamics, there are three kinds of systems. There's an isolated system, and an isolated system has a border that cannot pass matter or energy. So the system is really isolated from the rest of the universe. What's called a closed system is a system whose border cannot pass matter at all, but it can pass energy. So with respect to matter, the system is closed, and it's called a closed system. And an open system will pass either matter or energy. Now, with the Earth, energy from the sun flows into the Earth, and as the Earth warms up, it radiates more and more energy back out into space. There's a constant energy flow across the Earth, and there is no flow of matter. So in the Earth system, the transfer of entropy by moving matter is not an option. The only way entropy enters or leaves the Earth system is with the energy flow. So now energy from the sun passes through the atmosphere. It warms the Earth. The Earth emits energy into space in proportion to the fourth power of how warm it is. And eventually, when it gets warm enough, it's emitting as much energy as comes in. And at that point, the temperature doesn't change anymore. It's in what we call a steady state. The same amount of energy is coming in as is going out. So the temperature remains constant. So let's consider what happens when energy passes through a closed system. The Earth is a closed system, and energy is passing through it. Let's look at the energy is flowing from a high temperature source to a low temperature sink. And when it does so, it flows through a system. Now this could be any system, but consider if this is the Earth system. The Earth system is in balance. So the energy coming in is equal to the energy going out. And so the system temperature is not changing. So we have an inlet temperature of T1, Ti, I think is the way I called it, and an outlet temperature of T0. When I say zero, I mean TO, outlet. So the energy is coming in at a high temperature from a high temperature source, and it's leaving at a low temperature from a low temperature to a low temperature sink. Now let's evaluate the entropy in those flows. Entropy, as we stated at first, is Q over T. Well, Q in is the same as Q out because the Earth is in steady state balance. But Ti is much greater than TO. And so what happens is Q over TI is much less than Q over TO. Is that obvious to everybody? That when you, let's say you have energy coming in at, say, 10 degrees. You have Q over 10 degrees entropy coming in. And it's going out at, let's say, 5 degrees. You have Q over 5 degrees going out. Well, Q over 10 degrees is 1/10 of Q. Q over 5 degrees is 1/5 of Q. So you have twice as much entropy going out as you have coming in. Does that?
What's up there has the reverse.
Oh, did I get my? I think. You mean I have my carrots wrong? I have my carrots backwards.
Yeah.
I apologize. That's my fault. I never even noticed it. But okay, let's. I'll have to correct that later.
It's been a while since
So
we've been in a math
right. So as long as there's energy flowing through that system, the system is going to be losing more disorder than it's gaining. When a system loses disorder, it gains order. It becomes more ordered. So this results in a situation that's exactly the opposite of what the early thermodynamicists were telling us. They were telling us that a system had to necessarily get disordered and become useless. This is saying that in this particular kind of a closed system, the order tends to grow, and it will continue to do so as long as that energy is allowed to flow through there.
So it's closed from a perspective of matter.
Yes.
But open from the perspective of energy.
Right.
Okay.
So that means that because the Earth falls into that category, the Earth is always generating order as opposed to generating entropy. Now, entropy comes from the sun, and it's calculated as Q over 5,800 degrees, which is the temperature of the surface of the sun. And the entropy radiating away from the Earth is quantified as Q over 288 degrees. Well, when you do the math, there's 20 times more entropy escaping from the Earth than there is coming in from the sun. So the Earth is becoming more ordered all the time. And that's what Charles Darwin was talking about when he recognized that the Earth was evolving. Biological species are becoming more complex all the time. Now, my discovery or my feeling is that it's not just biology that's evolving. Climate is evolving, and we'll get into that further rather than get sidetracked now. But geology is evolving. But geology is so constricted. It's not chemically active like the rest. So it's a very slow process for geology to evolve. it's a little bit, it's kind of an intermediate rate of thing for the climate to evolve, and it's a little more rapid for biological matter to evolve. But actually, because of this thermodynamic relationship, everything on the Earth is evolving. So, what have we learned from this little group of things? When energy passes through a closed system, there's a strong tendency for the system to become ordered, not disordered like the originators of the second law would suggest. The amount of order in the system depends on the entropy balance. If a lot of entropy escapes, the system becomes ordered. If less entropy escapes, the system becomes disordered and passive. And I put activity on there. Where's that cursor? The system becomes ordered and active. Now, the second law says that every process in the universe generates entropy. Every activity that occurs generates entropy. So if there's a lot of entropy, the system becomes passive, and if the entropy can escape, the system becomes active again, and that's something we'll get into more of later on. But order and activity are to some extent the same thing, because order is a differentiation. If you have high temperature on your left and low temperature on your right, there's a certain amount of order there. There's more heat over here than there is over here. When they mix, you no longer have that differentiation, nor do you have the ability to be active. The differentiation is dissipated to the point where no more action is possible. That's the meaning of the word equilibrium, which I'll get to later. So now carbon dioxide in the atmosphere constrains the ability of entropy to escape the Earth. So the Earth evolves toward a less ordered condition when carbon dioxide is in the atmosphere. Now that's interesting, because what's bothering environmental scientists is not so much that the Earth is warming, but it's becoming less diverse. We're losing species all over the place. And the diversity of the Earth is a function of the order. When the Earth becomes disordered, it becomes dysfunctional, and it becomes less diverse. It becomes uniform. And biology is not about uniformity. It's about multiplicity of system variability.
Well, so my question is, if somehow or other all of this additional carbon dioxide could be created without destroying biodiversity, would we still have a problem?
That's what I'm getting to.
Okay.
But the problem, as I see it, is that climate scientists are convinced that carbon dioxide is the problem, and that if we can get carbon dioxide out of the atmosphere, everything will go back to normal, and we'll be okay. I'm concerned that's part of the problem, but not the whole problem. And I think climate scientists and all of the rest of us would be terribly disappointed if we got to the point where we finally got the carbon dioxide back to its original level, 287 parts per million or whatever it was, and and found that it didn't solve the problem. And I'm afraid that that's what would happen. So I think considering the second law of thermodynamics gives us other answers to the problem that I'd like to see us consider more of.
Dan? I'm struggling to understand active and passive as
Okay.
used in this. Can you expand on that?
An activity is a result of a differential of matter or energy. An electric current flows from a high voltage to a low voltage, and that's a differential. Air flows from a high pressure to a low pressure, and that differential forces the air to flow. It wouldn't do so otherwise. And the presence of a differential is an indication that there's usable energy in the system. And when the system gets to equilibrium, there are no more differentials, and that's the meaning of the term heat death. So
Term what?
heat death.
Okay.
Yeah,
Okay.
the early thermodynamicists used the term heat death to describe a system in which all differentials were exhausted, and there was no more driving force for any activity. And now we're back to activity, and that was your question. I'll say more about that as I go along. Maybe it'll answer your question, and we can certainly talk about it afterward. Now I have to get to my next set of slides, and now I want to go into a discussion of what constitutes order and disorder. So how we doing there? Did I get that up?
Yep.
But it's not covering the whole screen, is it? I may have to put up with that.
Go to slideshow
What's
Go
that?
to slideshow.
at the top.
Oh, thank you. Yes, all right. And then from beginning, there we go. Oh, you guys are geniuses already. I don't.
Just hold PowerPoint hands.
Right. So this is now about order and disorder. Now that we know a little. How is climate change related to thermodynamics? Well, in thermodynamics, there are two well-known laws. They're called the first law and the second law. And the first law is about energy. And the second law is about dispersion. How the energy is dispersed, or how order is dispersed. And I guess since Albert Einstein, we don't differentiate between order and energy anymore, because Einstein tells us E equals mc squared, so they're both the same. But anyway, the first law says that any system that's accepting energy, the energy flow into the system balances with the energy flow out of the system. that concept is missing the fact that the energy inside the system causes changes, and so the incoming energy and the outgoing energy may not be equal, but when you add the third term, which is the amount of energy in the changes that are occurring, then it balances. So now, when the Earth irradiates its warmth out into space, when it's warm enough to radiate as much energy out into space as is coming in, then the temperature doesn't change anymore. When the temperature of the Earth remains constant, the energy balance determines the overall average temperature of the Earth. Now that's how climate scientists calculate what to expect out of global warming. And they used to use that term. They finally decided that wasn't answering all their questions, so they used the term climate change. That doesn't answer all their questions either, but they're ignoring it so far. The first law describes these changes that take place when energy is flowing through a system. The second law is about dispersion. And the second law says that energy differentials, and for that matter, material differentials as well, become dispersed. They become equalized. It's the differential that drives any process. And so as a process occurs, it's equalizing the differential to the point where when the differential disappears, there can be no more activity either. Let's see. Our climate system is ordered atmospheric flow patterns that carry solar energy across the surface of the Earth, and I'll get into that in a minute. If the order is disturbed, those patterns change, and we can see great big changes in our climate. So what we have to be concerned about is changing that flow pattern, not necessarily increasing or decreasing it. So that's what the second law of thermodynamics is all about. Now this whole analysis is based on the second law. The second law says every process creates disorder. Well, the early thermodynamicists said that if everything's creating disorder, the fate of the universe is to become totally disordered. And it'll be a totally disordered condition, a chaotic condition with no distinguishing patterns, uniform with no differentials of any kind, dead with no activity. It's what they described as a heat death. Modern non-equilibrium thermodynamics, by the way, that heat death is what's called equilibrium. And let that sink in a minute, because we're going to get to argue about it later. Modern non-equilibrium thermodynamics sees it differently. A system can become ordered and remain ordered, and to do so, it must have the means to discharge the disorder that it generates. Systems may become ordered or disordered depending upon their ability to discharge order faster than it accumulates. To discharge disorder, excuse me. Our world is a complex ordered system that discharges more disorder than it can accumulate, thereby becoming more elaborately ordered all the time. And this I'm particularly fond of this argument because it flies right into the fray of the religious approach to things that says, you know, you have to have had a plan. Somebody had to be designing this whole thing. No, nobody had to design it. It just had to be a product of the discharge of disorder. Things start to become ordered.
So photosynthesis is a discharge? Photosynthesis, taking elemental materials and building them into a biomass.
Photosynthesis creates disorder as well. In fact, it creates more disorder than it does order. But the disorder discharges, and the order remains behind. And I'll get into that later too. That's an excellent point. So let's look at this disequilibrium Earth. I don't know how to shut that animation off. If I did, I would. But anyway, those are climate zones, and that's how the ordered Earth looks. Let's get the right-hand side of this chart out of the way first. If energy from the sun impinges on the Earth, and the Earth reaches a temperature where it's discharging as much energy as I didn't bring my little pointer along with me. As comes in, then the whole Earth reaches a temperature where the temperature remains stable, and that can be calculated, and it's 59 degrees Fahrenheit. And when you take that, we're going to call it the equilibrium Earth, even though that is a misnomer in terms. When the Earth reaches that temperature, it's stable. When we only consider that kind of equilibrium, the whole Earth is the same temperature. Now, what really happens is that let me bring this up. I think I can do this a little bit better. No? Oh, I know what to do. The energy coming from the sun is very high temperature shortwave radiation. And the entropy content of high temperature shortwave radiation is relatively low. And when that energy impinges on the Earth, it imparts that entropy to the Earth. So the energy coming in makes the Earth more disordered. But the energy that goes out is low temperature, long wave energy. And that energy discharge is a very high entropy. So the Earth is discharging more entropy than it's receiving. So entropy is disorder, so it's discharging more disorder than it's receiving. So the Earth becomes more ordered because it loses more disorder than it gains. Now when that happens, you don't get 59 degrees all over. What you get is circulation in the atmosphere. And the circulation in the atmosphere creates three climate zones. You have the tropic climate zone, the what do you call it? Intermediate climate zone, and the polar climate zone.
Temperate.
What did you call it?
Temperate.
Temperate, thank you, yes. So you have the same amount of energy, but it's not distributed the same anymore. And these zones circulate all the time. So all that activity is due to the fact that you're discharging more entropy than you're receiving.
So going back to your S equals Q over T.
Yes.
So how does long wave radiation have a higher entropy than short wave radiation in the context of
Yeah. Long wave radiation has a lower T, is a lower temperature radiation. High, and so the quantity Q over T is greater. Incoming shortwave radiation is high temperature radiation, so the quantity Q over T is smaller.
because T is a smaller denominator.
Mm-hmm.
Okay.
So, what do we want to cover? We want to think about what order is, and why things become disordered, and what happens to make something disorder. How does that happen? And if entropy always increases, how does something stay ordered? These are the questions that have had scientists at loggerheads with each other for centuries. How is energy related to order? How can we measure disorder? What are the characteristics of order? And I'll go into some of these things. What is complexity? Does order move faster than disorder? How is order related to biomass? We want to look at the energy balance of the Earth and the entropy balance of the Earth, and then although I've already said this, what makes the Earth evolve? And what makes the Earth evolve is there's an entropy balance, and we're losing entropy. So let's consider order. If you have a tray and a bunch of ping pong balls, and you take the trouble and the ping pong balls are two different colors, and you take the trouble to organize the ping pong balls according to color, that is a manifestation of order. And I think we can all agree with that. It's kind of a definitional. So that's an example of an ordered system. If you take a vibrator and attach it to the edge of the tray, so that it shakes this arrangement all back up again, you have something like you have in tray B, and you have the balls then all mixed up. That's a disordered system. Now, I want to make an observation here, because it's very salient to what the environmentalists are concerned about. Tray A, the ordered tray, has a diversity of environments. It's got 3 different environments. It has a blue environment, a red environment, and a white environment. Very American, wouldn't you say? The tray B has one environment. It's a red, white, and blue environment. But you can't go anywhere in tray B and find a different environment. It's all the same. So it's the disordered system that that has that lacks diversity. The ordered system is the diverse system. You have three different environments in this very, very simple example of an ordered system. And so my contention is the Earth is losing diversity because it's becoming disordered in this sense. And this happens to be related to temperature, and we'll get into that too. But this is one of the things that environmental scientists are most concerned about, is the loss of diversity in the environment. Let's see. Now, how do things become disordered? Well, if you take tray A, which is a very, very ordered tray, and you make it warmer, you add heat, all those molecules, or all those ping pong balls, begin to shake and shimmy, and they impact on each other, and they become mixed up, and that makes the system disordered, and on a molecular scale. When you also have molecules from the white zone, which is undefined, that can impact on the collections of molecules here and break them up. So you have internal disorder and you have external disorder. But temperature, heat creates the disorder that eventually breaks up that order. Now, so suppose you have something ordered. Suppose you have something disordered. How can it become ordered? Well, I've chosen as an example some glasses of water. And when you take heat Q out of the water, it begins to form solids and eventually ice. And the more heat you take out of it, the more solids form. And these solids are the more ordered form of water. So that the removal of heat generates order in your system.
I don't want to get on too much of a digression, but this is all making me think about the fourth phase of water.
Oh, yes. Well,
how
I can't be very useful there, I have to tell you.
it's really cool.
Yes. I have some trouble with some of those ideas. So I get to be, I'm not constructive, and I would prefer to participate in an argument I'm constructive about.
Okay.
So how does something stay ordered? Well, if you have tray A in an ordered sense, and it's becoming disordered, and you want it to fall back into the ordered state, you have to extract disorder from it, as you can see with this arrow. And it turns out on a molecular level, maybe on a ping pong ball level too. I don't see much evidence of it, but there's a tendency for these things to fall back into their ordered position when you extract energy from it. When you extract entropy from it, and entropy is just energy over T. So, you're very close there. But now, in order to keep a system ordered, because there's always heat around, and every system has a tendency to become disordered. In order to keep it ordered, you have to be able to discharge the disorder that you're generating into something else. You can't just make it disappear. You've got to have something else, something ordered to discharge it to. And in the biological world, if an animal wants to survive, it has to find some food, which is some ordered material. And after it eats the food, it puts its disorder into that food. The food becomes disordered, and it gets excreted here. And the animal, having taken the order from the food, survives as a healthy, ordered being. And this is true of the entire Earth system as well.
So in that model, the animal is also drawing energy from that food. So there's
Yes. But see, entropy and energy are so close to being the same thing. It's just that you can actually predict what's going on, how much order and disorder are going to result if you do it in terms of entropy and not energy. You actually, when you get to the point where you're actually assigning numbers to these things, you find that it makes a whole bunch of difference if you use entropy rather than entropy and an energy. So now let's consider some of the characteristics of order. Order is a function of fixed relationships between atoms and molecules. It is a function of molecular size, because larger molecules assemble more atoms into fixed relationships. Once those atoms are put together in a molecule, they're no longer free to move with respect to each other. They're in fixed positions. So that they are, in the same sense as the ping pong balls in the tray, they are ordered. They are therefore more ordered than smaller molecules. Because smaller molecules have no bonds between them, they can move independently. And that's what some scientists might call random. Smaller molecules move in random ways. Yes?
The larger molecules do have bonds between each other?
Yeah, they do. Yes. In fact, we'll get into some of that. Yes. Which makes them even more ordered. You know, you can't, once they are bonded, and they may be bonded in several places, they can no longer move with respect to each other. So instead of this big a molecule, you're talking this big a molecule. And all of these atoms are all fixed together. Larger molecules tend to be heavier than smaller molecules. So ordered molecules tend to be heavier because smaller molecules tend to be more like single or dimolecular, diatomic molecules. Solids, liquid, and gases. Solids are the most ordered. Liquids are the intermediate, and gases are the least ordered. And I drew this little chart of the tray with the on the bottom tray you have some extra depression where the red and blue ping pong balls are, and at low temperatures these ping pong balls tend to fall into those depressions, and they become ordered like that. When you warm it up, the solids not only expand, but they also become disassociated with each other, and it becomes a liquid and fills the next level. And when you heat it up more, you break all the bonds, and it becomes gaseous, and there are no more containing walls that'll hold it.
So, sorry.
No,
Just trying to get this. The previous slide, one of your points was around molecular weight.
Mm-hmm.
And does that ultimately function to create differences in density, which create order in materials? Because
Let's see.
why does it matter? Molecular weight in this context.
Maybe we'll get to that.
Okay.
And if I don't get to that, remind me, and we'll go back into it. But yeah, thank you for asking. I think. No, that's great. So the amount of energy that it takes to dislodge a molecule from a more ordered and probable location to a less ordered and more random location is given by the product of the amount of disorder produced and the absolute temperature of the system. Q is equal to ST. Well, if you just manipulate that, you get the definition of entropy, which is S is Q over T. So this equation tells you how much energy is involved in transitioning from a more ordered to a less ordered state. This is the energy that it takes to push matter from a more probable configuration into a less probable configuration. If we take that energy back away, the whole system tends to collapse back into the more probable configuration. So that like the tray with the depressions, the disorder of the phase change tends to be recovered as order as the system cools. So if we can measure that energy coming from or going to a system during a phase change, we have a numerical indication of the amount of order or disorder. So here it comes to having a way to mathematically identify how much order is in a system. Phase changes are step changes in disorder. This is the face of a melting glacier, and the energy from the sun and conductive energy from the air is melting the face of the glacier, and it's running away as water. By adding heat to this glacier, you're extracting you're adding disorder, which is disordering the molecules and creating water.
I can't resist asking you this.
Go ahead.
How do you account for the unique quality of water as being more dense in the liquid phase?
Oh, I'll answer you, but I'm not sure I'll be correct because it's been a while since I've looked at that. But I think in the solid state, it has to do with I know the water molecule is not linear, but it's bent, and they don't fit exactly together. so they take up a little more volume. So they're just a little lighter weight than water at 0 degrees centigrade.
Like a hexagonal structure.
So yeah, so it floats on the top. When that process continues, the water evaporates, soaking up more disorder, becoming disordered itself, and you wind up with a desert-like situation, and all the water in a vapor form. Now here, maybe this will answer some of your questions about complexity in small molecules and big molecules. The small molecule in the upper right, there are only 4 reaction sites on that molecule. And in fact, on that particular molecule, they're all the same. So there's not much except one reaction that molecule can undergo. But as a molecule grows in complexity, you get a large complex molecule, and that large complex molecule will have various reaction sites on it, and each site is a little bit different and may react with a different kind of molecule. But you might find that a reaction site down here can react very well with a reaction site up here. And in order to do so, it has to twist that whole molecular structure around so that they can meet. So the whole molecule, the shape of the whole molecule is determined by the reaction sites on the surface of the molecule. These reactions are quite predictable, and when something performs in a predictable way, you call it functional. And a molecule like that can function in a predictable way. A molecule like the small simple one just reacts randomly, because in the first place it's more rigid, and in the second place it doesn't have so many options of places it can interact with. Now I like this slide because that sign is taken off a vending machine that doesn't work anymore. Well, if it doesn't work anymore, it can't function, and function is related to order. That machine has one piece that's no longer in order. It's not necessarily out of order, but we call it out of order because it doesn't have enough order to work anymore. These larger, more complex systems function in a predictable way because they are ordered, and that's really the purpose of that slide. Now, order is so important to function that maintaining order is an existential issue. We can't exist without order. If an individual organism can't discharge enough disorder, it dies. If a species cannot discharge enough disorder, it goes extinct. If an ecosystem can't discharge enough disorder, it collapses. And if a planet can't discharge enough disorder, it can't generate life. It can't support life. But But we don't have to be completely out of order to be dysfunctional. Just a little piece, just a little protein with a misplaced nitrogen atom could make our bodies completely dysfunctional. So order is really critical in living systems. And let's get back to size. Larger molecules are more ordered than smaller molecules because they are anchoring a larger number of atoms into fixed positions with respect to each other. Well, when that happens, it also becomes heavier. And the heaviness and the mass of this large ordered molecule gives it a certain inertia and makes it a slower moving molecule than disordered molecules, which are relative lightweights. And the illustration at the bottom of this slide is meant to show a large ordered molecule and a bunch of tiny disordered molecules. The disordered molecules move about rather randomly. And when they impact the larger molecule, they bounce off. And the larger molecule is so heavy that it hardly responds at all. It just kind of stays there. So there is this mechanism that tends to separate order from disorder with respect to material things. That disordered things tend to dissipate and basically disappear. Ordered things tend to be massive and stay behind. So that's one example of a mechanism that makes ordered things kind of concentrate and disordered things dissipate. In biology, you have cell walls that are semi-permeable. And semi-permeable cell walls tend to let disordered molecules through because they are small and fast-moving. But they retain ordered molecules so that the material inside a cell wall tends to become more and more ordered all the time. And it tends to lose disorder by that mechanism. Now, if you couple that with a metabolism that takes on small molecules and attaches them together, then you have several of those small atoms growing into bigger, more ordered pieces, and you get order building up inside living cells and stuff. And I think this is a very clear example. Now the most ordered form of matter known is biomass. Photosynthesis takes carbon dioxide and water and puts them together to form a sugar, glucose, and takes the glucose molecules and links them all into a chain, a polymer that comes out to be cellulose. Now the molecular weight of cellulose is huge, which is why all this ordered material becomes solid and is a good structural material because it's so ordered and so fixed in place and fixed to every other atom in the whole mass. But if the Earth is to continue to generate that amount of order, it it has to discharge huge amounts of disorder. And that's where that entropy balance comes in. So now, once this order is generated, will it stick around, or are we losing it? In a natural system, the earth, some parts of the earth become forested, and that process produces a material that stays around long enough to grow. And the disorder from the photosynthetic process gets discharged as gaseous forms. A lot of it is used to evaporate water, and I won't go into that later, but that's a wonderful topic. But is the Earth really losing biomass? Well, here are some data collected from some work of some people at the University of Manitoba, and that first point is 20,000 years ago, at the end of the Wisconsin glaciation, and there's a lot of biomass missing there because the Earth has had all the biomass sheared off it by the action of the glaciers. When the ice age ended and the Earth warmed again, the biomass began to take over, and it grew to the point of the second point here. I can put this here, the second point here, and at that point, the growth began to level off, and it in fact retreated until this point, which is only almost modern. It's only a couple of hundred years ago, and at that point the bottom dropped off, and biomass has been plummeting ever since, to the point where it's way down here. Well, I found this graph to be fascinating. Each of these points represents a period of time when there was a major change in the relationship between human beings and the Earth. This one didn't involve human beings much. This was the end of a glaciation period. But this point represents the onset of agriculture, when people were harvesting biomass to produce open fields that they could cultivate agriculture in. And it was enough to kind of shave back the amount of biomass on the Earth. When you get to this point, this is when the steam engine got to be perfected, and people found that by cutting biomass and burning it in a steam engine, you could get your work done for you. And the amount of biomass that was required to fuel early steam engines was immense, and the amount of biomass on Earth has been plummeting ever since, and it's presently at this level, which you can find in textbooks around. It's about 650 gigatons of biomass. And what was fascinating to me is that we're also experiencing a problem with global warming, and I'll just keep that term. The globe is starting to warm. Well, back here, when the amount of biomass was similar, not the same, but similar, the climate warmed there as well. That's why the glaciers retreated. Now, this may be just coincidence. But I would almost be willing to bet there are thermodynamic reasons why, when the biomass drops to that level, you begin experiencing global warming or global equilibration, or call it whatever you like. So I think this is a fruitful area for more research. I want to just talk about the energy balance of the Earth. This is a NASA graph illustration showing the yellow energy from the sunlight coming into the Earth, and the red radiation from the Earth going out, and the two balance pretty well. So that's your first law of thermodynamics: energy balance. So the temperature of the Earth doesn't change because those are balanced. Okay, this is kind of a review. S equals Q over T. But what it's saying is that depending on the temperature, entropy varies a lot. So that entropy radiating out from the Earth, which is low temperature, has much more entropy than radiation coming in from the sun, which is very high temperature and has very little entropy. So here's a similar illustration showing entropy coming in from the sun and entropy going out, radiated with the radiation from the Earth. And you notice you have about 40, and I can't read the units, milliwatts per square meter per whatever, and the entropy radiating out is 940 milliwatts per square meter per degree Kelvin. I think that's what it is. Well, what is it showing you? It's showing you really that there's 20 times more disorder in the entropy radiating away from the Earth than in the entropy coming into the Earth. That's really a huge incentive for the Earth to become ordered and active. So I think that's a very strong argument for a thermodynamic entropy balance driving the changes that are ordering the Earth and are stimulating activity on the Earth. Another argument that I just kind of fabricated here was that in the Industrial Revolution, huge changes took place in the amount of activity on the face of the Earth. People began to learn how to generate activity, and you can't do that without a huge increase in the entropy. Entropy. Because entropy is generated with every process. So when humans began to generate all of these new processes and activities, each process and activity generates entropy. So the entropy level on Earth went up. So now the radiation of heat into the universe is not the only destructive force destroying the order of the Earth. Human beings are actively converting ordered products into disorder ever since the Industrial Revolution, and it's getting worse. It's why burning fossil fuels to create energy is destructive to the environment. But it's a little different way than people are used to seeing. You're taking all the order of the earth and you're destroying it to produce products and services that you like. But you are responsible for the ordered nature of the earth being converted into disorder. That's essentially global equilibration, and it's us doing it. And it doesn't necessarily have everything to do with energy. It just has us to do with our destructive tendencies, a willingness to destroy ecosystems in order to make our own desired function, and disrupt all the functions that are going on in the ecosystem. So that being said, why does the Earth evolve? Well, when you get disorder coming in at Q over 5600 degrees K, and energy going out at 288 degrees K, you have such a negative entropy balance that you are producing entropy faster than the Earth can get rid of it, and that's eliminating all the diversity and all the ordered functions. So our activities. See, climate scientists are looking at the energy relationships, but there are order relationships that need to be looked at, that as far as I know haven't been looked at, and I think we need to look at them more. So the Earth is losing disorder or gaining order all the time. That's why the Earth is evolving, but we're interfering with that. We are taking that order and destroying it for our own purposes, and so we're essentially making the Earth evolve backwards. You can think about that a while, but so the question is, can the Earth continue to evolve? And the answer really is only if it can discharge disorder fast enough. As soon as we block the escape routes for disorder, the Earth begins to accumulate disorder and become a disordered system. And the bottom item is when the Earth becomes disordered in this way, you begin to lose species. And it's the most complex species that die off the fastest. All of the megafauna, for instance, are virtually gone, except for a few places in the world.
But aren't the plankton, for example, dying off because of
They are too.
CO2?
Yeah. And it may be. I mean, I can't say that simple organisms don't have their relationship with the environment that makes them vulnerable.
Well, and then their die-off accelerates ours. So.
Yeah, right. So we're almost there. How how can we prevent the loss of complexity of the Earth? Well, we can keep the atmospheric discharge pathways open. That's what people are attempting to do by controlling carbon dioxide. But as far as I'm concerned, that's only half the requirement. We can stop destroying all the existing ordered systems on the Earth, which is basically the biomass inventory, which is why that graph is kind of plummeting down at the end. And but even those two things are not sufficient. We have to rebuild the lost ecosystems. We have destroyed more than half of the biomass. If you look at that curve, that downward swing at the end, we've destroyed more than half the biomass on the Earth. And we just, the Earth can't continue to produce order fast enough to keep up with us, unless we bring it back into some reasonable level with the original biomass. So this is a list of things that we've discussed. I don't know whether you want to hear it all over again, but basically that's what we talked about, and that's the end of the order and disorder portion. Next week, I want to examine thermodynamics and what thermodynamics says about what happens when you add heat, thermo, to material things, and what kind of dynamics are created. And after that, there's a discussion about how that applies to ecosystems and the environment.
Are you able to put the previous slide on the screen?
This one?
Thank you very much. Yep.
Can we get copies of your slide deck?
Say that again?
Can we get copies of your slide deck?
Actually, you know, I have made up some copies. I can give you some. We'll have to see each other. Oh, I could bring in some next week.
I won't be here.
Oh, that's right. Oh, that's a good time for me to bring them in.
I can go get my thumb drive
Well,
out of my car.
Well, I know where you live, and if you're coming, I mean that's an incentive to have you come back in the final week.
Oh, I definitely will come back.
Done with this slide.
But
If we're done with this slide, can you go to that last slide? 'Cause
I have a thumb drive in my car.
Oh, copy this. I don't know how to, but if you know how to, by all means.
You're going to take a break.
Yeah, we're basically done. 7:38. That's an hour and a half. I did pretty well to get through that material this fast.
That was really a lot of information in a very short period.
You got all the ideas. Anyway, it's really a very different approach, is it not?
Yeah, I mean it is, and it puts things in the right perspective for me, because it is, we're not saying that it's not important to draw down the CO2 and stop emitting greenhouse gases, but that the real nitty gritty is to restore ecosystems.
Mm-hmm.
And that also, if you go into the whole dynamics of it, that also helps to draw down the CO2.
Yeah. You know Dee Dee Pershouse and
Well, yeah,
Walter
yeah,
Walter
we're
Walter
all-
Yenna. I think this fits in beautifully with Walter Yenna's work.
Well, yeah, actually, and part of my ulterior motive for making sure I got here is that we're doing a presentation of the soil series at the Farm to Plate Conference on the 8th of November. And I volunteered to try to integrate some of this stuff into my presentation, in which I'm going to talk about the importance of biodiversity and cultural diversity and all the other kinds of diversity.
One thing I'm doing that's relatively new that I should have gotten into when we were looking at the red balls and the blue balls and so on. Adsorption of nutrients in soils, adsorption of mineral nutrients, is a thermal process. That just like
Not like about cation
Just-
exchange capacity.
just like if the sun shines on a glass of water, it begins to evaporate the water.
Yeah.
When the sun shines or the temperature goes up on a handful of biomass that's got, let's say, phosphorus molecules all anchored in place in it, the increase in the temperature releases those phosphorus molecules. And what that means is, in the spring, when the soil starts to warm, those molecules break off the biomass, the biochar, and they become available to the plants.
Yeah.
In the fall, when the temperatures plummet, the nutrients get sucked back up onto the biomass. So the biomass are kind of a bank.
So you're talking
For-
about biochar.
I'm sorry. I do that. I get carried away and I get my words mixed up.
This,
But-
I've always explained it by biological activity.
No, this is purely physical activity.
Ah.
But and anything that depends on adsorption is the same way. What do they call it? Cation exchange capacity is an adsorption process, and that does exactly the same thing. It just has a much lower capacity.
Oh, so
Is
as
that
the
because of
temperature
relative
increases,
sites?
Yes,
The
yes,
relative sites on the particle?
yes. Surface area and relative sites and.
so as the temperature increases, it reduces the cation exchange capacity, so it loses its minerals?
No. As the temperature increases, it activates the cations. They start to vibrate,
They start
and
to-
pretty soon they vibrate so hard they break away and they go into the soil.
Oh, okay.
And then in the fall they slow down so much that they get caught again.
Pyramids. Oh. Anyway, can we
And-
take a break so I can go get my jump
Sure.
drive and
So I come to this from a background in wastewater treatment where, we sought to maximize biological diversity in order to create the greatest stability in the system and also the greatest number of pathways to deal with complex.
Yes. Yes, okay.
And, I recall that the rule of thumb we used was for every 10 degrees Celsius plus or minus, you either double or halve metabolic rate of the system. So,
Yeah,
right, so that,
that rings a bell for me, but it's,
well, that
Yeah.
the warmer it got, the faster you could metabolize
yes.
wastes,
And-
which are
and of course
essentially
there are upper
nutrients and
limits.
energy.
Yeah.
And you know, it was essentially using chaos to create the maximum stability in the system. The more chaos there was, the more stable the system was in the face of volatile assault of inputs.
I just have a little trouble with those particular words, but chaos being equilibrium is stability personified. I mean that in equilibrium there's nothing but chaos and nothing can happen because there's no order at all. There's no driving forces. So that is the ultimate in stability. I just wouldn't have used chaos as my word, but
Okay.
the way you used it, I think it's absolutely right.
Okay. I haven't quite figured out Q over T yet, but I get it. I don't feel it, right?
That's okay. That's okay. I have this difficult time. Some people answer my written expressions on the web, and sometimes I answer them with all good intent, trying to explain exactly what I mean, and then they're likely to come back with even more questions and more doubts and more anxiety about what I've said, and there has to be a place where I stop worrying about it and just let them think the way they think and I think the way I think, and so I can appreciate that your concept of chaos is really in a lot of ways exactly correct. That's
Well, this conversation around cations is, is it physical, is it chemical, or is it energy? And I think it's really, how you view it. I view it as a chemical process that's, more likely to be active at higher temperatures.
Mm-hmm. Mm-hmm.
I guess I view all
Well,
metabolism as ultimately chemical processes,
yeah,
just happening in metabolic systems.
As you say though, all physical and chemical processes tend to go faster at higher temperatures. There aren't very many that show the reverse.
Can't think of it.
Yeah. So. Anyway, I think this is just a fascinating study, and I can't wait to carry it further next week.
Well, I will just mention that a member of our Soil Health Coalition, Judith Schwartz in Bennington.
Say that again.
Judith Schwartz.
Oh, I know. Yes, Judy. Yes.
Yes, her third book is all about people who have restored ecosystems.
Oh, she's incredible. I wish I could keep up with her. She's incredible.
It was her first book, Cows Save the Planet, that ever got me connected with all this.
Yeah, yeah.
But the nice thing is that ecosystem restoration is pretty incredibly accessible as a concept.
Yes,
to
yes,
most people.
and it's doable. We've been so many years thinking that you have to do things by machine, and really where ecosystem restoration has been most successful is where they've where they've done it by force of human labor. You know, it's
Labor,
human labor.
or
Yeah.
as Alan Savory, yeah, I guess you would call that human labor, setting.
Have you
setting
have
up
you
boundaries and restoring
have
them.
you have you seen John Liu's videos? There's a video by John D. Liu. He's a videographer of Chinese extraction.
Is it okay to close this slideshow?
Yes. Oh yes, by all means.
How do you spell lose?
Liu.
Oh, okay.
And the video is called Lessons of the Lus Plateau. And it's about this area in China called the Lus Plateau.
Right.
That's Loess.
Right.
And
And they restored it, right?
it's where the wind-blown soil from the Gobi Desert has kind of dropped out of the wind pattern in this area, and it's a huge area. It's the size of the country of France, so it's a huge area, and the agriculture there denuded the land, and of course, this is all wind-blown soil, so it all blew back up in the wind, and it's basically all gone, and it erodes through water erosion very easily. So the place looks like a moonscape, and they have restored ecosystems on that area.
So I have read.
Anyway, the video is just beautiful. I enjoy it. I've seen it a half a dozen times. But
I guess it's beautiful.
It's videography of the culture of the Chinese people in that area, and how their culture has been restored by the restoration of ecosystems. And it's phenomenal. Well done.